What's up? What's up? It's your boy Network. Y'all shouldn't have gave me this, man. That's gonna be my new intro. Anyway, today's topic is section 1.2b of the CCNP Route Exam, IPv4 and IPv6 Fragmentation. Now, this title is a misnomer because I'm gonna give y'all a little hint before I even get there. IPv6 don't really fragment. So really it's really about IPv4 fragmentation. So we're gonna go over a little bit of that. We ain't gonna do no hands-on today because mostly this is mostly theory. So strap on your thinking caps. It may get a little boring. I'm gonna try to keep it entertaining for y'all. Anyways, and like I said, I'm gonna try to cut these videos down to less than 20 minutes, so that way you can get in and out with your studying. You know what I mean? I'm gonna try to do a couple of these today. I had a lot of stuff to do. Anyway, let's get on right with the show. This is exam. We are still on networking principles, right? Section 1.3b, IPv4 and IPv6 fragmentation. After that, we're going to do TTL, which is 1.3, time to live. All right, so let's get on with the show. I'm going to tell y'all right now, this is not fragmentation, all right? This is a little internet meme or image macro that spawned from a meme. Don't feel so good. I'll leave y'all a link in the description if y'all don't really follow social media or you just live under a rock completely. Just some people, man, the internet, boy. Anyway, that's not fragmentation. So fragmentation is, yes, another Wikipedia definition. I don't care what y'all say. If I don't find it in Cisco, I'm going straight to Wikipedia. And Wikipedia, yes, it is, people can vandalize it or whatever, and it's editable by anybody. That's a real word. Anybody can edit Wikipedia, but for the most part, I want to say I never really seen vandalism. I had to get it pointed out to me in some articles, like when Donald Trump got president, people were all up on his page, whatever. But anyways, IP fragmentation is an IP protocol that breaks packets into smaller pieces or fragments so that the resulting pieces can pass through a link with a smaller maximum transmission unit or MTU than the original packet size. So we really need to talk about what an MTU is before I really start talking about what fragmentation is. So basically MTU is like the biggest size packet that you can fit through a link. Now, there's all kinds of technologies, different links and different sizes of MTUs. So you got Wi-Fi 802.3, you got PPPO over Ethernet. You got Ethernet, that's what everybody uses, fast Ethernet, gigabit Ethernet. They all got different MTU sizes. So basically, just think of like a pipe, and you got another PVC pipe or whatever, or something that is probably like a rock or something. You're trying to get it down a pipe, but the rock is too big for the pipe. So you got to get a smaller rock, and the rock size would be the MTU basically. So, or actually, yeah, the rock size would be the MTU. And the pipe size would be, that would be the MTU actually. The pipe size would be the MTU. And the rock would just be the size of the data, if that makes any sense. I always try to do these analogies or whatever. These are the common MTU values, right? Like I was mentioning before, you got PPPoE, you see that over there right there, it's 1480, PPPoE, 1480. These are all in bytes, by the way. You got token ring. I don't know why the token ring got bigger size MTUs. Maybe they ain't really, I don't know. I can't even call it because token ring is really older technology. But either way, the sizes of the MTU is bigger. Maybe I believe it's more efficient to have smaller data to get through. But you're going to find out later on that fragmentation is actually an old way of distributing packets throughout a network. This is probably the most common size MTU, which is 1500 bytes. Everybody uses Ethernet, fast Ethernet, gigabit Ethernet. You might not know it, but when you downloading a file and stuff like that, more than likely at your house, even in enterprise environments, the networking technology will be Ethernet. That's also the PPP default, as you can see. Hyper channel is the largest size MTU. Anyways, those are the different PVC pipes, the different sizes like a pipe, right? Now, these are the different visualization of the different technologies in networking, right? You got 802.13, that's Ethernet. That's also Wi-Fi. Then you got gigabit Ethernet. I can't really remember the sizes in kilobytes or bytes or whatever right now on top of my head. Fiber optic, which is probably the fastest along with hyper channel. Then you got 10 megabit Ethernet right here on the right hand side, right? So think about it. Remember, these are the pipe sizes, and you got only one size rock. In Ethernet, we got 1500 bytes to work with, right? So some of these pipes, right, might be too small for your rock. So that's where you have to take the rock. I don't know how the hell you're going to do it, but you're going to have to take the rock and chop it up, or use some kind of gravel grinder or whatever to make it go through the PVC pipe, because the rock is too big, if that make any sense. I'll be coming up with these strange analogies, but like I said, this is my way of kind of dumbing it down, or just trying to simplify it, even though it's, it's really complicated technology. This is technology that, I don't know how they came up with it, but this is just my way of kind of making it more simplified. This right here, if you remember in your CCNA studies, this is the actual Internet Protocol header. So when you send in a packet, so when you send in a packet over the Ethernet, this is the header. This is kind of like when you send in an envelope, this will be the stamp, if that make any sense. Because you got, as you can see, you got the source address, you got the destination address, so it's kind of like the from and to, right? And then you got these other, flags and options and all this other stuff. We'll get into all that other stuff later in other videos, like time to live and the version. Well, actually, the version, there's only two versions. You got IPv4 and IPv6. Remember, we ran out of IPv4 addresses, so we had to come up with something called Network Address Translation, which is NAT, which stands for Network Address Translation. That was a way for us to kind of recycle our IP addresses, if that makes any sense. And the future is IPv6. So those are the two versions that would fit in this little flag right here, or this part of the header. But for now, we just gonna focus on this row that got that's really the fourth bit right here. This orange row, these are what they call flags, right? And this part right here, the fragment offset, and also the total length, because all this fit in the total length, the 16 bits. I'm gonna get a little bit into the math, but I ain't really that great at math. It's simple math, but I'm gonna try to kind of break it down for y'all, a little simpler. So anyways, back to this IP header. We gonna use this analogy, right? So we got the envelope, right? This is the IP header is the envelope, and then the source address and the destination address, that's all on the envelope, right? The contents will be a data payload, which is attached to this right here. It's gonna be on the inside. We also got these puzzle pieces that we're trying to send to our friend, right? So the puzzle pieces are inside, and the fragment offset right here where it says fragment offset, this will be kind of like, because we want him to kind of put these puzzle pieces together, because we had to break down the rock, kind of, so to speak. So instead of the rock, we're using the puzzle pieces. If you want to ship rocks, we could do that too. We don't want to ship rocks. We don't want to do that. We gonna ship puzzle pieces. So we put all the puzzle pieces in the envelope, or a little package, because it was too big or whatever. And a fragment offset will be kind of like the numbers we put on the back of the puzzle pieces. That way it's easy for him to kind of organize it. So then we got these two little things called the flags, right? I don't know if I'm pointing at that. I don't know if y'all can see. These two right here, these are called the flags, right? The first one, that's the DF bit. That stands for don't fragment, right? So even though we fragmented it, more than likely, if you're going to have to fragment it, we're not going to use the DF bit. The DF bit is going to be used in path MTU discovery. We're going to go over that later. And it's also used in IPv6. They don't fragment. I'll tell y'all right now. Like I said in the beginning of the video, actually, IPv6 does not fragment. It uses path MTU discovery. Now, the next bit, the MF, stands for more fragments. Actually, let's go back. Let's go back to the DF. So that stands for don't fragment. If it's set to 1, that means the packet is dropped. We know not to fragment it, because we opened it up. You got a 1 on here. Don't fragment. Well, you know what? F this. We're gonna throw it away. And then we got the MF bit, which is more fragment. That lets somebody know when he receives it, okay, there's more coming. There's more puzzle pieces, because he only shipped me a couple. If it's set to 1, that means more is coming, right? Now, if it's the last puzzle piece, it's gonna be set to 0. So we don't open it up. We see the MF bit is 0. We're like, okay, we got all the puzzle pieces. This last piece. Or it could be that it's the only fragment. You get the envelope, we open it up, we see the puzzle pieces, and the MF bit is set to 0, this also could tell us this is the only fragment. We ain't got no more coming. Either way, it's no more coming. Because if the first one come, right, it's going to have a 1, letting you know there's more coming. If you just get a 0, you know that this is the only one. So it's fragmented, but it's the only package, if that makes any sense, right? And the fragment offset, like I said before, that's like we kind of cheated to help him out. We put numbers on the back of the puzzle pieces, so he know, okay, this is the first puzzle piece, this is the second one, this is the third one. That's called the offset. I be thinking some, like I said, I was gonna make a lot of hip hop and basketball references. Like I said, those are my interests. So that's the fragment offset, right? Now we're gonna get into breaking down what happens when you take these packets and it's going through the network or whatever. I wanted to kind of show y'all in Packet Tracer, but I don't remember if the fragment and stuff, if it gets broken down or if it really show you. So anyways, let's say, looking at this, we got over here in the gray, that's obviously the router. This 2700 is going to represent our packet, right? It's 2700 bytes. Now, let me go back. I forgot to tell y'all. The ID just let y'all know, okay, it came from, well, not who it came from. Yeah, it's who it came from. So it's like when I'm sending an envelope, it's my name on it, right? The address will be the source address. The address will be the source address, and then the destination address. But the identification, it just lets you know well, the source address is gonna let you know it came from me, but it's kind of like that's my name on it. So I'm shipping it, and you're like, oh, this came from network, bro. Right? That's the ID. These are just arbitrary numbers. Don't, you know what I'm saying? Don't get too hung up on it. It ain't gonna always look like that, like with a 0x and stuff like that. Now, every IP packet, everything you send, anything you download, they're gonna have the header, which is 20 bytes. As you can see on the right hand side, it's 20 bytes plus the data, which would be the payload. So whether it's your email or your image that you just sent somebody, whatever, you got the 20 bytes on the right hand side. You got these 20 bytes right here. That's the header. This whole thing right here is the header. And then you got the data length. So that's why we have to divide it. The 20 and then the 2680, which gives us the 2700 bytes of data. Now the offset, y'all remember what I told y'all what the offset was, right? This 0 mean we just doing it right now. Always at the beginning, this is the first packet. It's more coming. Or it could be that it's the only one. But remember, now look at this. You see where it's MTU right here? We got in the middle. The MTU is 1500. So that's the most common size maximum transmission unit, especially with Ethernet, right? So since we trying to send this this packet is 2700 bytes. Router can't get it through past this link because it's 1500 bytes. So we got to break this up, right? We can't send it. We got to break this. We got to fragment. And notice also the MF offset just lets you know where in the puzzle pieces this kind of aligns. But it's going to be a number. You got to take your MTU and divide that by 8. And that's going to tell you. I'm going to send y'all a link on that really kind of explains it too. And the reason why you got to, why the number got to be divisible by 8. And that's going to give you your offset number. But right now the offset is 0 because this is the first part of the packet, right? And then the MF means if it's a 1, remember, the 1 lets you know it's more packets coming, right? And the 0 lets you know that it's either the last packet or the only packet, last fragment or it's the only packet. Now, since we had to break this up, as you can see on the right hand side, I was going to stop to let y'all do the math, right? If you want to go ahead and pause it right now. But so we got the 2700 right here. And we had to break it up in 2 pieces right here. We got the 1500 size frame or the 1500 size packet. And then we got the 1200 size packet. Both together give us 2700. Why we had to break it down in these 2 pieces? Why couldn't we just split it in half, right? Well, that's why it's the maximum transmission unit. We're going to try to maximize the size of the link. So, okay, fine, 1500, we're going to send 1500. And then whatever we got left, that's what we're going to send. And you do the same thing if it's bigger. I'm going to show y'all another slide. So, again, on this part right here, see the ID. You got the header length is 20, data length is 1480, the offset is 0, letting us know that this is the beginning. It's the first fragment, because the first fragment has an offset offset of 0, right? And then the 1 let us know it's more coming, right? That's why the MF is 1 on this. Now, the second one, the header length is also 20. The data length is 1180. Why couldn't it just be 1200, right? Because the header length, remember, the envelope, it's like it's 20 cents for the envelope, kind of, if that make any sense. And then we got the data length, which is 1180. Now, the offset, this is where I kind of sometimes get confused, right? The offset, how we figure that number out, the offset, the way we figure that out is by 1500, which would be the MTU, minus the header, which is 20. See there where it say header length? We take the MTU minus the header, divide that number by 8. That gives you the number that the offset is going to be. In this case, since it's 1500, right? We take 1500 minus 20, which is going to give us 1480. I'll get a whiteboard on here. So 1500 minus 20, that gives us 1480. And then you divide that number by 8. That gives you 185. So that's the multiplier you're going to use for every other offset. And then that lets the receiving end know what part of the puzzle this piece lies. So since the first offset right here is 0, the next offset is 185, right? So then we just going to add 185, and that tells us the next offset plus 185. The next offset is 370. And then the next offset going to be plus 185. That gives us 555. That's going to be, so then in this case, you're going to have 0. Write this down now. 0 for the offset. And then the second one is 185. Next one is 555. The next one is plus 185, 740, and so on and so forth. You just keep doing 185. But that's just an identifier for the receiving end and let them know, oh, okay, this is the third piece. And the next one's going to be like, okay, this is the fourth piece, and so on and so forth. I don't know, why couldn't they just be like piece number 1, piece number 2, piece number 3? It's really because of the math of the IP header and stuff like that. So if you really want to, really look into that, don't get too hung up on this math, because I don't even think it's this kind of math that you got to do on the exam. But like I said, this is just one of those things that you just got to know. So, or should know rather. Let's go ahead and do another one. I'm telling y'all right now, I didn't like algebra. I didn't like no kind of math. And this is simple math, but this is just part of the stuff that you gotta kind of know. You gotta know how packets travel throughout the network and stuff like that. So, all right. So this next one we're gonna do. Okay. So we got 4,600 bytes on the left hand side, right? That's our packet, right? Again, the ID is just a number I came up with, and it's just letting you know who it came from. The header length obviously is 20 bytes. Remember, 20 bytes right here. That's the size of the IP header. And then the data length is the size of the data minus 20. So in this case, 4,580 bytes, right? The offset is 0 because this is our first piece. And then the more fragment, which is the MF bit, is set to 0 to let you know whether this is the first piece or only piece. So I'm going to go ahead and let y'all figure out the math. You can pause it right here and let y'all do the math, right? MTU again is 1500. All right, so since 4,600 bytes is too big, we got to split this up in a couple pieces, right? We already know, just by the looks of this, you can see we got to divide it into 4 pieces for it to fit through the pipe, if that makes any sense, right? Well, I don't know what you'll be doing sending envelopes to a pipe, but so 1,500 for the first piece, right? The header length is 20, so 1,480. I took out the ID because that's always going to be the same. I also took out, I didn't take out the header length. It's also going to be the same on all of them. It's always going to be 20 bytes. 1,480. Offset is 0. MF, the more fragment bit, let you know, hey, there's more coming. The first one was 0, let you know whether it's the first one or if it's more coming. But nobody didn't get it yet. It just came in, let you know whether it's the first one or if it's the only one. So when we spit it out, the next router, these are the fragments it's going to get. Now, we go back to this slide right here. When you sending it through the network, right, it's going to be broken up in little pieces or whatever because it needed to. It's the receiving end that's going to put the puzzle pieces together. Not these little routers right here. If we left it up to these routers to do the fragmentation, this is going to cause so much, stress and workload for the CPU. It's the end host that's going to put the puzzle pieces together or rearrange them back together. Now, let's go back. Now, look, the only thing really that changed, if you look at all of this right here, other than the more fragment bits, like let you know, hey, it's more coming, hey, it's more coming, hey, it's more coming, and then this last one is 0. This is the last piece, right? But also the offset kind of tell you that too. Well, no, not really. The 0 lets you know this is the first set. 185 lets you know this is the second set or second piece of the pie, kind of. That's the third set, and this is the fourth set. And then it's just going to, all these pieces just going to go flow through the network, and the end host is going to put all of these pieces together. And it knows how to do it by looking at the header length, data length, offset, and the more fragment bit. Now, none of these got remember this flag right here, the DF, because we're fragmenting. If we weren't fragmenting, it's going to have the DF, and we ain't got to worry about all this. But, this is actually the old school way of sending packets throughout the network. Fragmenting. We don't even really kind of do fragment. We kind of do, we kind of don't, but for the most part, this is not what's really used today. I'm gonna go over that in the next couple slides. This last piece is 100 because that's what was left over, right? So 1500 is 3000. That gave us 4600 right here, and then this last piece was the 100th bit. This data length, I think that's wrong. I should have made this. This should have been 80 actually. That data length right there, because remember 80 plus 20, that's going to give us 100. So that's a typo right there. Here's this last, we're going to do one more. This is the last one, I promise. Look over here on the left-hand side where the packet is. That's, I don't know what, million bytes? Billion bytes? I don't know. I don't feel like counting all them zeros. Either way, I figured out a way to figure out that's 1 gigabyte of data. So y'all go ahead and do the math. This is a little harder. Go ahead and pause here. All right. So anyway, like I said before, the ID is just an arbitrary number. The header length is 20, right? And then there's the data length. That number minus 20 set is 0. Or fragment bit let you know is 0. So this is the actually this should have been that was the first piece. Now when the next guy gets it, it should be 1 because that lets you know it's more coming. So here go the answer. I took out the ID and the header length, because that's all going to be the same, right? The data length is 1480. See, that's going to be the same on all of them too, because these are all going to be 1480, because it's 1500, 1500, 1500, 1500, 1500, 1500. It's going to be 1500 all the way to maybe the last piece, right? And then the offset, just keep going up. Remember 0, 185, 370, 740, 925. The only thing that's really going to change the offset number is the maximum transmission unit. So if you change that, and I ain't feel like doing all that because it's just 1500 that's the most common type of network you're gonna run into is Ethernet, and the maximum transmission unit size is 1500 bytes. So that's why I was just working with that. You just keep going and keep going and keep going. I'm not gonna do all that math, but at least you kind of understand the pattern, and that's what this was about. And lastly, IPv6 fragmentation. I don't know why I left that slide blank. So yeah, in IPv6, the routers never fragment the packets, right? They just don't do it. That's the old school way of doing that. I'm sorry for showing y'all that, but that's just, yeah, we deserve that right there. You made me do all this math, and we don't even use this. Anyways, you got to understand like the history of it. That's why there's RFC documents that you could look at, and you got to know where you came from to know where you're going. You wouldn't even know about, you wouldn't even understand IPv6 if you don't understand IPv4. Maybe these new millennials, when they get born, and they like, IPv4, y'all only work with this many IP addresses? But anyway, so yeah, IPv6 routers, they never fragment the packets. They use this thing called PMTUD, path method. What was it called again? Path MTU discovery. So I'm going to explain all that. It's actually a whole nother section dedicated to that. I don't even know why you can see that's even on, you see right there on 1.4a. That's going to be in the next couple of videos. That's when we're going to go over that. What actually happens with IPv6 fragmentation, they all have the DF bit. it just says don't fragment. It lets everybody know don't fragment this. Don't fragment this packet. Instead, you'll get a message if something is too big, like if the rock is too big and it needs to be, and it feels like it needs to be fragmented. What's going to happen is you're just going to get a message right there where it says packet too big. It's a type 2 message. Basically, the packets just drop. You'll just get that message. So it's going to use PM path MTU discovery to figure out how to send this packet, and we're gonna go over that in the next couple videos. So, anyways, I know it's a lot to kind of go over. Don't get too hung up on the math or whatever. That's the last slide. The next video is gonna be about time to live. They should have made it. They should have put that in order, but this, I guess, that's a TCP operation. So, if you like this video, go ahead and like it. Hit the like button. Comment, please. If I made any mistakes, let me know so we can discuss it and stuff. I don't really know everything. I just try to break some of this stuff that I kind of know down. And go ahead and hit the subscribe button right there. I don't know if it's gonna be on the left hand side or it's gonna be on the right hand side. I'm gonna start doing annotations and stuff and fancy stuff. I'm just trying to get this out to the world. Go ahead and subscribe to the network.